Hello and welcome back to Calculus 1 section 3.7, the chain rule, which is probably the most important derivative technique because this technique deals with derivatives of function composition. Derivative of function composition, where you take the couple of functions, you nest them all together, right, into function composition, and then you take the derivative of it. So let's take a look at why something like this is needed. So when you have the derivative of, let's say, 2x plus 3 squared, it's easy. You can FOIL and then just deal with the polynomial. So that's going to be 4x squared plus 12x plus 9, and then you just have your 8x plus 12. So it's possible to take that derivative, but you had to do algebra to FOIL because we don't really have the technique to deal with something like this, which is function composition, right? It's x squared, and then 2x plus 3 is kind of nested inside of x squared. So we didn't have the method to deal with that, which is the chain rule. So instead we FOILed and then we did this. But now if I ask the same problem and now I say the power is, let's say, 38, right? Are you going to sit there and FOIL this, right, to the 38 power and go through that? It's not impossible, but it's going to take quite some time. The numbers are going to be ridiculously large, obviously, and you're not going to have too much fun. So how do we deal with derivatives like this? Now, what should be clear immediately is that this particular function is decomposed with f of x equal x to the 38 and g of x equals 2x plus 3. So they together can make f of g of x, which is what we call function composition. You might have seen it in this form as well, f composed with g. So we would like to learn this method. Now you would still say, well, brute force would still do it if I, make myself go and do the, 2x plus 3, use algebra, and multiply 38 of these, right, straight up, it's still possible. And the answer to that is yes, it is still possible. But what if you get e raised to the cosine x, right? There is no algebraic witchcraft that you can use to plow through that one. So we need to figure out the way to take the derivative of function composition. So chain rule is derivative of f of g of x, or whatever, right, function composition. So what's the rule? The rule is the derivative of f of g of x is the derivative of the outer function with g still plugged in times the derivative of the inner function g of x. There is another way to write this as a chain, which usually no one uses it, but the book does push it, and I've noticed enough homework questions, right, from students over the past that I know that the book and the MyMATLAB really push the other notation as well. So I'm going to give that one as well, and that's the derivative of f of g of x is df dg times dg dx. Now you can see that this is the derivative of f, and you can see when dg cancels, you can see the derivative of f in respect to x. So we still see it in this notation. As I said, MyMATLAB and the book really push this notation, but in my never humble opinion, the formula on top is the easiest to work with, because it literally deals with like a layers of onion, where you have the outer function and the inner function and all of that working together. So I would like to immediately show the way I think about these things. So let's go and have maybe cosine x raised to the 6th power here. I just want to use two different functions. Now, yes, I should have written this as a cosine x to the 6th this way, but it's kind of hard to see, right, the function composition there. So I'm just going to write it in this form because it's easier to see function composition. Now, what are my functions here? Well, what I call the outer function and then the inner function, right? The inner function is plugged into the outer function, which is the first function that you meet when you look at the problem. So that outer function f is clearly x to the 6th, and the inner function is cosine x. So when you plug g into f, you are replacing every x of f with g. You are replacing every x of f with g. Every x of f with g. So you are technically getting g to the 6th, which is cosine to the 6x. So we know that this part here where we decompose the function, we know it's good, it's solid, because we just checked it. All right. Now, the way we take these derivatives, we take the derivative of the outer function, which is 6x to the 5, and multiply by the derivative of the inner function, which is negative sine x. Now remember that every x over here is going to be replaced by g. So if I go in the problem and I say this is one big X over here, what is the derivative of x to the 6th? It is 6 times x to the 5. But I don't get to write x, I get to write g in it. And then times the derivative of the inside function, which is derivative of g, which is derivative of cosine is negative sine. So that's the way this derivative works. You take the derivative of the outer function with g plugged in, and then separately you take the function of the inner, derivative of the inner function, and you get your negative sign. Now you can make this all pretty, negative 6 sine x cosine to the 5x, and you can make it even prettier, but we don't care about that now. Let's take a look at another example. There's going to be like 100,000 examples. We're done with the theory. You either know the formula or you don't. You need to understand how to use the formula, especially if you have very bad skills with function composition. You're not going to have fun time in Calculus 1 or 2 or 3, especially in Calc 3. So if you have problems with function composition, my suggestion is to spend about 2 hours there without even looking at this homework, because nothing here will make sense if you can't decompose functions, preferably mentally. Let's take a look at another problem. square root of x cubed minus 2x. There we go. So, can anyone tell me what my outer function is and what my inner function is? You have to unmute yourself.
Is the outer x to the 1/2?
Excellent.
And the inner is x cubed minus 2x.
Perfect. Very good. So I need to take the derivative of x to the 1/2, which is a square root, right? So that's going to be 1 over 2 square root of x. So if I have to take the derivative of square root of x, the answer is 1 over 2 root x. Now remember, this x is not x, it's g. Therefore, this x cannot be x, it must be g. So this has to be x cubed minus 2x. The form of the derivative is the same, but you are no longer using x. Now you are using whatever function was there. And then finally times the derivative of the inside, which is 3x squared minus 2. You have to put this in parentheses, obviously, because it has to multiply everything. So you can make this prettier, right? If you just put 3x squared minus 2 divided by 2 times the square root of x cubed minus 2x. And that would be, maybe I can actually fit this over here, right? Perfect. Okay. 2x. Let's see another example. The derivative of e to the x to the 4 minus 2x plus 6. And I will let you work this out for about 20 seconds. If you have the solution, just say it. Yep, the YouTube comment got it. So we are going to do the same. We have f, which is just e to the x, and g is this polynomial x to the 4 minus 2x plus 6. So we know that the derivative of e is itself, but remember, we can't put e to the x, we put e to the g. E to the g, which is the whole thing, and then times the derivative of g, which is 4x cubed minus 2x plus 6. And this works out to be 4x cubed minus 2x plus 6 times e. I mean, we didn't do anything other than reverse the order. That's the way we always write, right? The polynomial first, then the exponential. If you had a trig, then there would be a trig next, and so on. Awesome. Good job. Let's take a look at more of these. How about the derivative of tangent of x squared plus 1?
Professor, for the previous problem, where did you get the polynomial? Like,
Polynomial is given to you, right? Oh, you mean in the answer?
yeah, 4x cubed. Where'd you get that?
Well, this is your f prime and this is your g prime from the formula.
Yeah.
Oh, 4x cubed, 2x. Oops. You're right. I didn't pay attention. Yes. Okay, good. Someone is paying attention. That was a good catch. Our g is this. The derivative of g is 4x cubed minus 2. Derivative of 6 is 0. All right, good. So all we have is 4x cubed minus 2 e to the x to the 4 minus 2x plus 6. Okay, good. So here is your f prime with g plugged in. So g is unchanged. And here is your g prime, which is the derivative of the function g. So now the same will carry here. You have your tangent x outer function and g x squared plus 1. Very good, Paul. Should I say, I was testing you all, and yeah. So make sure that the g is the derivative. I took derivative only in the first term. I didn't take the derivative of the second two terms, so that's where the mistake was. Up, the chat on YouTube again has it correctly done. Yes, that's perfect. So we take the derivative of tangent. That's secant squared of x. But we don't put the x here, we put the g here. And then times the derivative of the inside, which in our case is just 2x. So you have your f prime with g plugged in, and then you have your g prime. So altogether, these two happen to be 2x secant squared of x squared plus 1. So that was really good. Now let's see another example. We keep coming up with more and more examples. So let's see something from homework from the book. All right, even though this is going back in complexity, that's fine. Cube root of x squared plus 9. Let's see how that goes. The narrative on the chat on YouTube is correct. The story of the derivative, we can call it that way. Is anyone going to offer the solution?
I got 2x over 3x plus 9.
3x. Wait, you should have the fractional exponent because you are taking away 1 from 1/3. But it's close. It's close.
No, but like what I did was It was like in the fraction, I got x2 plus 9, so I just square rooted the x and square rooted the 9.
Oh, no, you can't, because there is a plus in between. No, that's not allowed. Okay. So, then the intermediate step was correct. So once we break this apart, we have 1/3 of g to the negative 2/3, because we have 1/3 minus 1. 1/3 minus 1 is negative 2/3, times the derivative of the inside, which is called a chain, right? So that's a 2x. And now we say, okay, what are all of the things that go on top? That's going to be 2x. And everything that goes at the bottom is 3x squared plus 9 to the 2/3 positive now, because we pushed it in the denominator. And this is where it ends. This is where the whole thing ends. You could put this as a cube root to get rid of that fraction exponent, but it doesn't really matter. This is as far as we can go. All right, let's make this now interesting. The derivative of sine cubed of x squared minus 3, whatever. What is so new or important about this particular example?
Do we got to use product rule?
There is no product rule here. This one is the argument of sine. So those are not two separate functions, right? There's no times in between, because you always have to have sine of something. In this case, it's sine of 2x minus 3. Oops. So that's all like one unit. It's not a product rule. If you had sine x times x squared minus 3, then it's a product rule, because they are all independent functions. Sine without anything here is not a function on its own. It's actually a religious term. It has nothing to do with math, right? So it's not a product rule in this case. Can anyone else see?
There are 3 functions.
There are 3 functions. That's it. Very good. There are 3 functions. I'm going to rewrite this to write it as sine of x squared minus 3, and then I'll put everything cubed. So now we see that the outer function f is x cubed. Then we dig one level in, and that's going to be sine x. And then we dig one more level in. So it's like, peeling the layers of the onion. So we actually have 3 functions. And the chain rule doesn't care how many functions you have. It will always operate derivative on this level, derivative on this level, derivative on this level. Multiply them all. So you can have 15 functions, one inside the other. The chain rule will still apply the same. So, people say, well, what's the formula? It's completely irrelevant what the formula is, because you take the derivative of f with g of h still plugged in, then you take the derivative of g with h still plugged in, and then you take the derivative of h at the end. So 3 functions, 1, 2, 3 derivatives, you have 2 chains right in here. So the amount of functions will tell you how many of these, right? You will not be taking derivatives forever. I've seen some students, keep taking derivatives until they until exam shuts down. No. What we do is we take the derivative of the outer function. In this case, that's going to be 3 of something squared, right? Because that's what the derivative of, my derivative of x cubed is 3x squared. Now, we don't plug in x in. We plug in the whole, what I call guts, all right? Plug in the guts of the problem. So that's going to be sine of x squared minus 3. Then times, now the next one, the derivative of sine is cosine x. But we don't put cosine x. We put the, again, guts of that sine, which was this. And finally times 2x at the end. So all of this simplifies into 6x sine squared x squared minus 3 times cosine x squared minus 3. And now there is the full answer. So we had 3 functions this time. And a lot of problems in your textbook have 3 functions, even more. Let's take a look at another example of this monstrosity. Let's see what else is. Well, let's just try problem 55 because it looks cool. It says the derivative of sine to the 5 of cosine of 3x. You immediately start counting the functions and trying to figure out how many you have and all of that stuff. How many functions do we have? Can someone tell me that at least?
4.
4 functions, very good. 4 functions. X to the 5 is the first one. 3x is the last one. So we have 4 functions. Good. Okay, let's take a look at the problem together. So we said 4 functions. Can you please tell me what are the 4 functions that we have in this case? F is what?
X to the 5th.
Very good. And then G?
Sine X.
Perfect. H?
Cosine X.
Excellent. And R?
3x.
3x. Good. So the derivatives are 5x to the 4, cosine x, negative sine x, and just 3. So we should be able to work all of this out. Actually, I'm going to move this on a side. And let's get the answer. Derivative of x to the 5 is 5x to the 4th. Now, what is x? It's this sine of cosine of 3x. Now we need derivative of sine. Derivative of sine is cosine, but we have to plug in cosine 3x. So we took this derivative of sine, is a cosine, and then its guts are here. And then we take the derivative of the inside now. That's going to be negative sine, and then use the 3x copied, and finally times 3. So our 5th power, right, turned into the 5x to the 4th. Then sine derivative is cosine. Then go one step in. Derivative of cosine is negative sine. Then go one step in. So it's always like this. You step in into the function. You take the next derivative. You step in, takes the next derivative, all the way to the end. Now you do not go past 3 because you already have your 4 derivatives. Here's the first one, here's the second one, here's the third one, and the 4th one. So 4 functions, 1, 2, 3, 4 derivatives. Please don't submit to me exam 2 with all 0, 0, 0 answers for every single chain rule. All zeros because you keep taking derivatives until you lose, right? Just make sure that you have 4 functions, you have 4 derivatives. I do have 4 derivatives here. I am done. Actually, we can make this a little bit nicer by placing negative 15 in front. And then we have our sine to the 4th of cosine 3x times cosine of cosine 3x, and finally times sine of 3x. That's just making it a little bit there. So good. And I'm looking at yep, the YouTube is on fire. I mean, those of you watching on YouTube, doing very well. So we can nest this as far as we want. Now here's a little bit of a challenge question. See if you can make your way through this. The derivative of square root x plus square root x. This one is spicy. The squeaky chair. I can see the questions coming in. And yeah, it's a lot of mess. It's not a product rule, right? And now how many functions do we have? Sometimes it's beneficial to start your derivative inside out. Sometimes it's beneficial from outside in. So far we did all outside in. I mean to decompose, not to do derivative, but to decompose. Now in this case, right, we want to see what we can do to figure this out. So let's at least write the functions. Do we all agree at least that root x is the outer function? We should not be dwelling on that because there is just a square root of some mess inside. So that's a root x on the outer. And now going into g, it is x plus root x. And the reason for that is that these are two independent terms. Just like, you had your polynomials, x to the fourth plus 3x minus 1. They're all three independent terms. When you take the derivative, you take the derivative of all of them at the same time. But it's not actually, it's very tricky here that when you take this derivative, right, you will have to worry about another root x derivative. So take the derivative of the outside, which is 1 over, right, this derivative is 1 over 2 root x on the denominator. So 1 over 2 root of the mess times the derivative of this, and that is 1 plus 1 over 2 root x. And now we place all of this onto the same, like 1 plus 1 over 2 root x divided by 2 root x plus root x. So now we do some algebra. So this is we can say times 2 root x times 2 root x to get the values, right? To get the double fraction out. So that becomes 2 root x plus 1, because this will distribute to both, right? Distributes to both. The first one multiplies into 1, giving us this, and the second one cancels completely, which is why we did it, to eliminate that double fraction. Now here, clearly, 4 times 4, I mean 2 times 2 is 4. And then this root x goes and multiplies the inside, so we're getting x squared plus x root x. And we can leave it there. You really don't have to rationalize because we don't know what x is. I mean, x could be 4, and if x is 4, then all of this nicely simplifies. So I would not simplify it further because I don't have the value for x. So we can leave it like this. We have to stop here. My office hours started like 5 minutes ago. So I'm going to switch to my Zoom link for office hours. Those of you with questions and interest in further developing this, stop by there. We are going to have a part 2 of this on Wednesday. So have a great day, and join in office hours. Link is in Canvas if you're interested to continue this. And I'm going to post the homework even though we still have a lot more chain rule to work on. Bye.